So we shall continue on, and so today we will work with, I'll do one last thing from chapter 7, just this little section, and then we'll do stuff on categorical variables, and then next week we'll do ANOVA, it's like, and then the week after we'll do regression, then we'll have a review week, and then the final exam. So it's, we're getting there, okay? And yeah, so there's a lot of content. I think this is why people complain that the final exam is hard. I don't think it was particularly hard. I think everything's straightforward, much like the quizzes. It's just that there's just a lot of stuff. So, but anyway, okay. So today, our last bit for comparing two groups of numeric variables. Two groups, but using a numeric variable. Okay, and so far we've done t-test, or independent groups. And the t-test for paired groups, or paired data. Alright. Both of these depend on the t-distribution, which assumes the application of the central limit theorem, or basically things follow the normal distribution. Okay, so this is the t-distribution. Do you guys remember the conditions that are necessary for applying the central limit theorem? Okay, so we have a few conditions, okay? Yeah, so the first one, and probably most important, is that your data was obtained randomly, or there's an assumption of independence when you select the individual data, okay? Kind of difficult to pull off, but that's the first one, okay? And then the second one we have what? Okay, the sample size not too big. And the third one is sample size not too small, right? Sample size being not too small is either population is normal, or sample size is large, right? Or sample size big. Okay, so this is all reviewed, right? And, okay, so far these things have, when we're comparing numeric variables from two groups, there is an underlying assumption that the central limit theorem holds. Okay? But sometimes when we look at data, it seems like we can't use the central limit theorem. Okay? So there are cases when we don't want, when these conditions aren't met. Okay? So sometimes we can't apply the central limit theorem. Okay, so what do we do in cases like that? Okay, so in those situations, we can't use the t distribution or the normal distribution or any kind of distribution, right? And so there's an entire branch of statistics devoted to figuring out tests and the properties of data when these types of when you can't assume some kind of distribution there. Okay? Yes.
I was just going to ask, is there some general rule to know whether you can or can't assume?
Yeah. So I'll talk about that just in a moment here. Okay. So so sometimes we can't apply the central limit theorem. We can't. These conditions aren't met. So we can't use the central limit theorem. So there's a whole branch called non-parametric statistics. Okay. And it comes from non-parametric statistics. That comes from the idea that when you have a normal distribution, you have to define the mean and the standard deviation, which we call parameters of the normal distribution. Okay, and same idea for the t distribution. So pretty much any type of distribution where we have basically a mathematical formula that creates it are defined by parameters. Okay, and so that's the parametric, I guess, family of statistics. And there's a whole branch of non-parametric statistics. You can take entire courses or several courses on non-parametric statistics, and today we're going to probably spend maybe 30 minutes on it, okay? And so you're just getting this very, very shallow introduction to this topic, but it's so you guys know that it exists, and so when you're ever faced in a situation where, I don't know how much data you guys will be analyzing in the future, but maybe you'll come across a situation, or maybe you'll see someone else analyzing data and presenting things, okay? And one thing you should ask yourself is, does the central limit theorem make sense? Does it make sense to apply the central limit theorem in this case, okay? And if so, then yeah, they can go ahead with a t-test and things like that, okay? Sometimes it doesn't make sense, okay? And in those cases, you probably need to use non-parametric statistics, which don't put the same assumptions on the data, and maybe you will say, okay, well, I don't know a lot about this, but this thing doesn't seem correct. Okay, so non-parametric statistics. Okay, so we use when we can't. So at least for our topic, it's used when we can't use the central limit theorem. Okay, so we use these. We use this when we do not want to make as many assumptions about the data. Etc., etc., etc. Okay. Yeah, these last few weeks, each week it's like the topic that I'm teaching you. You can take an entire course on that one topic that we spend, just 1 week or just one class session on it. And this one we definitely, we're just spending just a very brief chunk of time. Okay. So the test we're learning is called the Wilcoxon-Mann-Whitney test. Apparently, three different people worked on this and came up with this test, and they wanted to all get credit for it. Okay. And this is what our book teaches. It's equivalent. If you ever take another statistics class, it is equivalent something called the Wilcoxon rank sum test. Okay. It's not the same test, okay? Because when people were, I guess, discovering these new tests, okay, they came up with this and they thought, oh, this is great, okay? And then, I don't know who did whatever first, but then, you know, same Wilcoxon guy, he came up with the Wilcoxon rank sum test, and it turned out that, you know, when we understood the math part of it a little bit better, it turned out that it's pretty much the same thing, just they look a little bit different, okay? So sometimes you'll learn this. I think this is taught a little bit more commonly than Wilcoxon-Mann-Whitney, but they're both just fine. Okay. Yes? Signed rank test? No, signed rank test is for paired data. That's in chapter 8, right? Okay. Yeah, Wilcoxon-Mann-Whitney test and equivalent Wilcoxon rank sum test. This is for independent data. Yeah. Okay. So, all right, and so this is still in chapter 7. We are comparing a numeric variable between two independent groups. Okay, and you will want to use this again when you cannot apply the central limit theorem. In terms of tests, the t-test is a more powerful test than the Wilcoxon-Mann-Whitney test, okay? What does it mean for a test to be more powerful?
More precise?
Hmm?
More exact?
Not more exact, okay? So remember, what is power? Do you guys remember what the meaning of power is?
Probability of committing a type 2 error?
Beta is the probability of committing a type 2 error. Power is the probability of not committing a type 2 error, right? So power is the probability of detecting when you're supposed to reject the null hypothesis when the null hypothesis is false. Okay? So a more powerful test, if the null hypothesis is false, a powerful test will detect that it's false quite often. Okay? A less powerful test will say, I'm not so sure, right? Because our conclusions are, I'm rejecting the null, or I don't have enough data and I'm not sure, right? Those are our two conclusions. So a powerful test will say, here's the data, I'm going to reject the null, okay? And it says that I'm not so sure, less often, okay? But I mean, when the situation is that you're supposed to reject it, okay? So when it's less powerful, it's not strong. I guess you can think of it as, I don't know, if you're watching a race from really far away, right? Let's say you go to the Olympics, but you're in the nosebleed seats up top, okay? And so you're looking down and you're trying to see, you know, who won the race, okay? So one is you can look, you can just be squinting, but if the race is close, maybe you can't really tell, okay? But if you bring a telescope to the stadium and you're focused in on the finish line, you can tell who won, you know, more accurately, okay, if it's close. So I guess with your vision being more powerful, you can detect that difference. So the Wilcoxon-Mann-Whitney test is not as powerful as a t-test because you're not putting as many assumptions about the data, okay? So by using the central limit theorem, we're placing assumptions about the distribution of data, that either it follows that the population is normal, or that our sample size is big enough where our data follows the normal distribution, the sample mean follows the normal distribution. Okay? But here we're not doing that. Okay, so we're comparing a numeric variable between two independent groups. So this doesn't work for paired groups. Okay, and again, we are not placing any normality assumptions on the data. that this key in assumption that's still in place is this random and independent. Okay, we're still assuming that the data that we have is selected randomly. Okay, that seems to be an assumption that's very difficult to escape in statistics. Any kind of statistical test, it seems very difficult to escape that assumption. Okay, we still assume. Data selected randomly. Just because if you're not selecting data randomly, then you can say anything, right? You can always pick out unusual people and unusual things to try to say, try to convince someone, but so that seems to be something we can't escape. All right, so this is how it works, okay? So the key tip-off for when you want to use the Wilcoxon-Mann-Whitney test, okay? So the I guess typical scenario. This is when you don't have an extremely large sample. Even within the sample, it appears that some outliers exist. So, if you take a small sample and there aren't very many outliers, maybe it seems like we can assume a little bit of normality. Okay? But if it seems, if you're taking a small sample, 20 or less or something around there, and it already appears that you've got outliers, then that's a pretty good indicator that your data is not coming from a normal distribution. Okay? So some outliers exist. Okay? In one or both of the groups. Okay? So within the sample, it appears that some outliers exist in one or both groups. Okay, so that's your typical scenario for these. Okay, so this is how we do it. Okay, so here is the example is in the book is that we've got. So here's group 1. That's called growth. So this is so what they did was they. This data came from, I don't know, some forest, okay? I guess so they went into the forest and they're measuring how much carbon dioxide the soil is giving off, okay? Apparently this is interesting to some people. I'm not sure what what you do with that data. But anyway, they want to know, is the amount of carbon dioxide given off by the soil significantly different in two different regions of the forest? One was where there seemed to be heavy growth, and then other is where the forest was a little bit more barren, and it's called the gap in the forest. And so they measured the soil, and they were just trying to figure out how much carbon dioxide is going on. Okay, so you know, our numbers are going to appear a little odd. So these are the numbers, and what's there? 3, 15, 22, 190, and 64. You don't have to copy these down. These are in table 7.10.1. Okay. All right, and then group 2 is the gap. And the numbers we have there are this. Okay, so we don't even have the same number. Group 2 has 8 measurements, and group 1 has 7, and that's fine. Okay. The hypotheses we have to write out. Okay, we can't, because these are non-parametric. There's no parameter. There's no symbol. There's no mu. There's nothing that that we can really write to kind of summarize this up. Okay. So the null hypothesis is that the respective populations of our, the respective populations do not differ in the distribution, okay, of data, or in our case, soil respiration. Okay. So your null hypothesis is basically that the distributions of the data. So we don't know what the distribution of the growth data looks like, or the distribution of the gap data looks like. Okay, we don't fully know. But our null hypothesis is that the distributions are essentially the same. Okay. And then the alternative, okay, so the non-directional alternative would be that the distributions are different. Okay. So if it were non-directional, and the directional alternative is that, you know, the population 1 tends to produce larger values than population 2, or population 2 tends to produce larger values than population 1, however you want to say it. Okay? I mean, these are generic, kind of generic null and alternative hypotheses. Of course, you can make it more applicable to the situation by saying something like the soil respiration numbers in the growth section tend to be larger than the soil respiration numbers in the gap section. Okay, but that's pretty much saying the same thing, right? Population 1 tends to be larger than population 2. Alright, so here we'll continue our test as using the directional alternative. Okay, so in our scenario we will use the directional alternative. And the direction being group 1 or population 1 tends to be larger than population 2. Alright, so here's the steps that we do, okay? So first, we got to put the numbers in order, okay? So group 1 and group 2, we put the numbers in order. And so, we start off with 17, 20, 22, okay, and so, you know, these numbers are, it seems pretty clear that group 1 tends to produce larger numbers than group 2, okay? But this, but the Wilcoxon-Mann-Whitney test, you know, allows us to, without putting any assumptions on where the distributions that the data is coming from, allows us to kind of come to some kind of conclusion. Alright, so once we put them in order, what we do next is we go for each number and we count how many in the other group are smaller than that particular number, okay? So I look at the number 17 and I go to group 2 and I count how many numbers in my data set are smaller than 17. So I go 1, 2, 3, 4, 5, okay? So I have 5 numbers that are smaller than 17. I do the same thing for 20, and I have 1, 2, 3, 4, 5, 6. Up to 18 is smaller than 20, but 22 is not. So I have 6 numbers that are smaller than 20. Okay. I do the same thing for 22. Anytime you have a tie number, it counts as half. Okay, in terms of adding this up. So here I would go 1, 2, 3, 4, 5, 6, 6 and a half. Okay. If there was another 22. It would go 6, a half, and then the other 22 would also be a half, and so it would be a total of 7 numbers, okay? So each time there's a tie, those numbers count as halves. So here, I have 6 and a half, and then at 64, all 8 of the numbers are smaller than 64, so I write 8, and I do the same for all of these, okay? So the interesting thing about the Wilcoxon-Mann-Whitney test is that once you're past the largest number over here, these numbers don't contribute any more than this particular number. So it doesn't matter that this is 315. It could be 1,000, and would still contribute 8 points towards whatever statistical calculator. Okay? We do the same thing on the other side. Okay. So how many numbers are smaller than 6? 0 and smaller than 16. 0 numbers in group 1 are smaller than 16. At the number 18, I've got 1 number that's smaller. With 22, I have 1, 2, and then I have a tie. So I write 2 and a half. And then with 29, I have 3 numbers that are smaller than 29. Okay. Is that alright? Non-parametric tests are weird, okay? Alright, so then I add all of these up and I get 6 and a half over here. And then over here, I add all of these up and I think I get 49 and a half. steps, let me just write these real quick. Put in order, put the numbers in order. Alright, for each number, count how many points in the other group are smaller. Okay? Ties equal 1/2. And then add up those columns. Okay? And so at this point, what we do now is we take the larger of the sums, and that's going to be our test statistic. Okay, so here my test statistic is equal to 49.5. Okay. Some other textbooks that use the Wilcoxon-Mann-Whitney test will say use the smaller one, but it doesn't matter. Our book says this, and our tables are set up that way. So our test statistic is 49.5. Okay, and use the larger sum. The last thing is we look it up in the Wilcoxon-Mann-Whitney table. Alright, and so what the Wilcoxon-Mann-Whitney table says to use that one, we've got to figure out how many numbers we have in each group. So here I've got 7 numbers over here. And here I've got 8 numbers over here. Okay? So I think I've passed it out in your packet of tables, and if you don't have your packet of tables, I do have some extra table packets. This should be one of them. Okay. So here you take the larger end, and that's going to be the first number you look up, and then you go to the row with the smaller end. Okay, so I'm going to find 8, and then I'm going to go to the 7. Okay, so I'm about, I don't know, 2/3 of the way down the table, and I'm in this row 8, 7. Is that okay?
The higher 7?
So I take my larger number, n equals 8, and I start there, and I go to the 8 right there, and then within the group of 8, okay, I find the 7. Okay, so I'm going to go to so it starts off with 8, 8, 2, 8, 3, and then I go down to 8, 7. So I'm in that row, okay, and this one is set up so that it gives you critical values, okay? It says, so if you did this test, okay, and your critical value, or your test statistic ended up being 40, your p-value would be 0.189, okay? And if you did the test and your critical value ended up, so going further down, if your critical value ended up being 48, or test statistic was 48, your p-value would be 0.021, or your, I guess, tail probability would be 0.021. And if your critical test statistic was 50, your tail probability would be 0.0093. Okay? So our critical value was 49.5, so our tail probability is going to be in between 0.021 and 0.0093. Is that good? So, so probability is between, less than 0.021, but more than 0.0093. Okay, now here's the I guess the weird thing that throws people off, okay? Not that this test wasn't weird enough already. Okay, here we're using a directional alternative, right? So, for whatever reason, the publishers decided to put the non-directional values in this table, okay? So here we have a directional alternative, and it says it at the top of the table, okay? To get the directional p-value, you take these numbers and you divide by 2, okay? Assuming, okay, anytime you have directionality, anytime you have a directional test, the first thing you have to do is what? You have to check directionality first, right? Okay, so assuming that the directionality check passed, to get our p-values, we would take these numbers and divide by 2. So my p-value is going to be less than 0.021 divided by 2, so that's 0.0105. And then 0.0093 divided by 2, 0.00, I don't know, 461. Is that okay? So I took this and I divided by 2 to get this. Okay, so this is divide by 2 because it's directional. Alright. How am I supposed to check directionality here? Okay, in a weird thing like this where I can't compare the means and be like, oh yeah, the sample mean over here is larger and the sample mean over here is smaller. To check the directionality on something like this, you just take this statistic, okay, this 49.5, compare it to the 6.5, and this one is larger, and it's for population 1, so it matches our directional alternative that population 1 tends to be larger than population 2, because the sum of all the numbers on this side, like, because this is, basically you can think of this as how many of team 2 did this person on team 1 beat, right? So if you think of this as like, I don't know, some kind of wrestling match or, I don't know, weightlifting competition, right? So somebody lifted 190 pounds or something, okay? How many people on team 2 did they beat? They beat all 8 people. So you know, this is basically the total number of victories that team 1 had versus the number of victories team 2 had. Okay, so clearly team 1 had more victories than team 2. Okay, so in that case, our directionality checks out, so we take our p-values and divide by 2, or our our probabilities and divide by 2 to get our p-values. Okay, what do you do when the directionality check doesn't work? What's that? Yeah. If your directionality doesn't work out, you would just say our data doesn't support the alternative hypothesis. Okay, so that would be, you know, if I said, you know, does our data show or give us evidence that the gap produces more carbon dioxide respiration than the growth area? We would say no. Okay, our data does not support that. And in this case, does our data support that growth tends to produce larger values than gap? Directionality works out. Our p-value is tiny, so we say, yes, we have evidence that the soil in the growth areas of the forest tend to produce more carbon dioxide.
Where did you get the point? Can you speak for a second? Where did you get the 0.0105?
I did 0.021 divided by 2. Oh, did I not do that right? No.
Wait.
0.0105. I think that's right.
Oh, never mind. I wrote it the other way. That's why. I was like,
okay.
wait, I'm so confused.
Yeah. So
No,
everyone's okay with getting these numbers from the
understand.
table, right?
Got it.
Because my test statistic is in between here and here, so my probabilities are in between there.
You like to write it with a smaller number on that
I
side,
do,
and I
I
wrote it
do.
the other way, and I was like, where did you get
That's
that?
my I don't know, habit of learning
Yes.
math,
So
right?
I just got
But
I got
smaller
you.
numbers go on the left and larger numbers go on the right. That's just
Your
it's
way.
a habit I have a hard time breaking, and it throws off students every quarter. So that's just that's my habit. So Okay, so that is basically how you conduct the Wilcoxon-Mann-Whitney test, okay? If you're asking who came up with these numbers on the table, right? So these, this is always the hard part in the class, right? Because it seems like all of our tests are like, do this process, go to this table, which is magical, and get a p-value, okay? So this comes from the idea that so again, if we think of these as players on a team and they're like competing against each other, okay, and basically it's like a round robin, okay, each player's versus others and how many victories do you have, okay? So if you, the null hypothesis states that there's no difference between essentially the two teams, okay? And so what the null hypothesis, the way we came up with these numbers is basically if we threw all 15 players into a bag or whatever and mixed them up and randomly assigned the teams, okay? Randomly said you're going to be on team 1 and you're going to be on team 2. And we just did this a whole bunch of times, we can figure out the probability how often would one team end up with 49.5 victories and the other team ending up with only 6.5 victories. Does that make sense? So it's as if we just said we're going to just randomly assign teams, and then we say okay, and we're going to see which team wins in terms of how many people did you beat on the other team. Then how often will we get something extreme like 49.5 versus 6.5? Okay, because most of the time, if it's completely random, we would expect about an equal number of victories for both teams, right? I don't know if this is making sense.
Well,
Yes.
but so those comparisons are made on a one-to-one basis. If they're one datum compared to one datum, it's not like
No, it's not. This is basically, these numbers is basically like a round robin, right? This is, here is player 1 on team 1 earned 17 points, okay? How many people did that person beat on player 2, okay, or on team 2? Basically it's this versus this, he wins. This versus this, he wins.
yeah,
This
that's
versus this,
like,
he wins.
that's
Yeah.
it's a one.
So it's you're comparing this to everybody, and you're comparing this to everybody, and you're saying how many people did you beat on the other team, okay? And I could illustrate this with deck of cards, things like that. It's just if we were to randomly assign the teams, how often would we get an I guess a ranking like this, okay? And the probability of this happening just by random assignment of teams, the probability of that happening is very small, okay? It happens less than 1% of the time, okay? Whereas when you get kind of more equal balancing of victories and losses, then you know that's more likely to happen. Okay, but again, it's a less powerful test because it doesn't put any assumptions on the numbers, and it's just saying, you know, was this larger than this number or not? Okay, and so it doesn't matter that this was 315 or 10 million. Okay, it just says you beat all 8 people on the other team. Okay, so yes.
Whereas for the t-test, that would matter because you're computing all the statistics, you're using, say, the averages.
Yeah.
Or, well, at least the averages for the non-paired. So a much larger value would affect the average in a way that isn't represented here at all.
This doesn't represent the average.
Yeah,
Yeah,
there's no
there's
average
not.
here, right? We're not calculating means yet. On a t-test, you're comparing the sample mean versus sample mean, okay? And so extreme values would affect that. But if you do have extreme values, that also throws off your standard deviation, and it basically throws off the assumptions that you're placing on the data about things following the normal distribution. Okay, so this is what we use when we can't put those assumptions on. And again, there's an entire courses, entire field of statistics devoted to this. This is really all we're going to get into for non-parametric statistics. There's a little bit more in chapter 8 when dealing with with paired data, and you come across with non-parametric situations. Okay, there's like the sign test and the sign rank test and all of that stuff. Those are also non-parametric versions that we use for paired data. Okay, we're not going to cover that in our class. But, I just want to let you know that that exists. Okay, questions on this? Okay. My fear is always that because we're doing so many different tests, that this class is just going to feel like
Crazy.
here's a test and here's a test, and not really. I don't know. I think my goal is for you guys to appreciate data and recognize that different situations require different ways of approaching our thing. But I don't, you know, it's hard to teach that within just a short course like this. Okay, and we don't get to actually see too much data ourselves. Okay, so I'm gonna move on. Let's figure out how to do this. Okay, so we're gonna do chapter 9 and chapter 10. Okay, and they're very closely related. And this is we are now moving away from numeric data, and this is all dealing with categorical data. Okay. So this is I should say categorical data inference with the chi-squared test. We've already, did we, oh no, we haven't. Okay. We've done we had a little bit of categorical data experience, okay? You guys know what I'm talking about? So dealing with probability issues for categorical data, that came up when we were dealing with the binomial distribution. The binomial distribution, we're dealing with a count, but for a categorical variable that produces either a yes or a no, a success or a failure. Okay, and we were able to say, you know, what's the probability that you get, you know, 55 or more coin flips if we flipped a coin 100 times. Okay, and we could answer that using our normal approximation to the binomial. Okay, and so that's a test that exists, but we're not going to really fully develop that. Okay, in this case, yeah, we got the categorical data inference with the chi-square test, and then we also have just confidence intervals or a proportion. Okay. Our book does something unique when dealing with confidence intervals for proportion. I think most introductory statistics classes just creates a confidence interval in a simpler manner. Our book does something slightly unusual, but it's not too hard. Okay, so our book uses something called the Wilson adjusted proportion. Okay, so P squiggle P tilde, okay, this is equal to the, I guess the number of successes plus 2 over the total number of observations plus 4, okay? So normally, usually, when you observe categorical data, you would use P hat is equal to Y over N, right? So if you observed 100 people and 60 of them had brown hair, your P hat would be 60 divided by 100, 60% had brown hair, okay? The Wilson adjusted proportion does something weird, and it says we're going to add 2 to our numerator and add 4 to our denominator, okay? And what that does is it's like adding in dummy observations, okay? It's adding in dummy observations in that if we were looking at something very extremely rare, okay? So if we, I don't know what's rare, but so let's say we were looking for millionaires, okay? And let's say we surveyed, we took 100 random people, okay? All right. So we were looking for the 1%, right? So we take 100 random people, but we didn't happen to get any millionaires in our sample of 100 random people, okay? So our P hat would be 0, okay? And if we were to try to make a standard error using a P hat of 0, we would run into problems. We would get no standard error. And then we would come to the wrong conclusion that there are no millionaires out in the world, okay? So what the Wilson adjusted proportion throws in is says, okay, well, let's not just say, let's not say there's 0 millionaires out there, okay? Let's just pretend like we interviewed 4 more people and 2 of them happen to be millionaires, okay? So we would have a total of 2 people out of 104, okay? So that adjusts our proportion so it's not 0, okay? And it does the same thing on the other end of the spectrum, okay? So we say, okay, well, let's go around and see, you know, how many people have 10 fingers, okay? And you go around, you ask 100 people, do you have 10 fingers? And maybe all 100 of them say yes, okay? Does that mean every single person in the world has 10 fingers? No, okay? So the Wilson adjusted proportion says, okay, let's add 4 more people and say 2 of them had 10 fingers and 2 of them did not, okay? And so your total would be 102 out of 104 people having 10 fingers, okay? And so that it kind of adjusts the thing that you're dealing with, okay? So that's our P tilde, and we make we can make a 95% confidence interval. For P. So P being the proportion in the population. Okay, so 95% confidence interval for P. And what we are going to do is we're going to say P. We are 95% confident that P is between P tilde plus or minus 1.96 and plus 4. Okay. And so alright, so let's just try out a simple example. Okay, so we'll say what percentage of people are millionaires? Okay, so let's try this out. So let's say we interviewed 100 people and we have 0 millionaires in the 100 random people we selected. Okay. because that could happen. Okay? It's also possible you select 100 people and you get a few millionaires back, right? So assuming we selected these people at random. So here, our P tilde would be 0 plus 2 over 100 plus 4, and that's basically, I should have just picked 98 rather than n equals 100, or 96. 96, I should have done that. Okay, let's see, 2 divided by 104, so I have 0.0192. Okay. So this is going to be 0.0192 plus or minus 1.96 times the square root of 4. So technically in the calculator I'm not rounding off at all, but I don't feel like writing all 8 decimals there. I think I did that right. Let me just check. Okay, and multiply that by 1.96. So 0.0192 plus or minus 0.0264. Alright, so let's try this out. I do 0.01, Okay. So here, this is what I get from my confidence interval. I'm getting a negative number here. Okay. Sometimes that happens when you're on the extremely low side. Okay. Obviously, you cannot have a negative proportion, so you got to put 0 on that side, and then your upper end would be 0.0456. And I would say I am 95% confident that the proportion of millionaires is between 0 and basically 4.56%. Or that the, if I'm going to use proportion, I should use a proportion here. Okay, and that's all we can say if we've gathered 100 data points. Okay, so it's important to remember that, of course, you cannot have proportions less than 0 or greater than 1.
That 1.96 is from where?
Oh, yeah, that's just part of what we use. The 1.96 comes from the normal distribution, okay? If you look at the normal distribution and you're looking for the middle 95%, you would use positive and negative 1.96. That's where our 1.96 is coming from.
Oh.
Okay?
Oh, it's one of those, well, not,
It's a critical value from the normal distribution.
okay.
Okay? And technically, we could do other percentages, like a 90% confidence interval and a 99% confidence interval, but that would require us to change this number and also the way we calculate our Wilson adjusted sample proportion, okay? Because we would not use y plus 2 and n plus 4, we would use y plus some other number and n plus some
So
other
do
number.
we always do 95?
Yeah, so to make our lives easy, we're just gonna stick with 95% here. So
1.96 all the time.
yes, for a 95% confidence interval for P, 1.96 all the time.
Okay, but so let's say if it was 90% would be a different number, but we're not gonna be working with that.
Yeah, we're not gonna be working with that because that would change other stuff. Okay, it would change your P tilde and n plus 4 and stuff like that. You can read about it in the book, okay, if you are interested, okay? It's, 95% is so, I don't know, kind of common in our, in the literature these days, so we're just gonna stick with that. I'm not gonna try to change the way we do statistics and confidence intervals, okay? And again, if you take another course and you make confidence intervals for P, then you probably will not use the Wilson adjusted proportion. Okay? And I think that's something fairly unique to our book. It's not that this is bad, okay? This is probably better than the classical method using P hat, but it's less commonly taught. Okay. Is there a question? Okay, why don't we take a little break there and then finish out chapters 9 and 10 really quickly, I guess.